very happy. I'm very happy to introduce our next speaker, Marie Jameson. She will be talking about Wronskians of graded dimensions.
Thank you. Thank you so much for inviting me. It's really awesome to be here because I hadn't realized this until yesterday, but my last in-person talk that I gave was also at Vanderbilt in I think it was late February 2020. And so that was the last talk before pandemic time.
The last person who was, I thought it was.
Yeah.
Goldfeld, but maybe it was you.
No, it was me because I came after Goldfeld. Yeah. And so it like feels good to have Vanderbilt be like the frame for that crazy pandemic time. So yeah, happy to be here. So I want to talk about Wronskians, and I've been trying to get a hold of some various ideas here for a while. Sharon Garthwaite and I are sort of trying to figure stuff out. I asked for a shorter time slot because I don't know the full story of what we're going to know. So I just have like a little tidbit for you today, and hopefully there'll be more that I could say maybe in some future conference. So I want to talk about Wronskians of graded dimensions. Oh, what do I click to make this go?
Yeah, and now the keyboard.
Okay. So the Qseries that I want to talk about today come from the theory of vertex operator algebras. And so these vertex operator algebras are objects that give rise to so-called characters of the irreducible modules. These are like, graded things, and each piece in the grading has a dimension, and so that gives us the coefficients in some Qseries. And so oftentimes if you have a sufficiently nice vertex operator algebra, then you'll get like a set of these Qseries called characters that span some modular invariant vector space. And so what you do in this situation is you look at Wronskians of those characters and things like that. So I'll define this W and W prime on the next slide, but there'll be Qseries built using Wronskians. And so it turns out that if you look at this quotient and call it F, then that can be interesting from a modular forms perspective. Okay, so what are these Wronskians? So if I just give you a set of Qseries F1 through Fn, then what you do is you put them into this matrix where the ith column has all of the derivatives of F sub I. And so here are the derivatives that I'm talking about Ramanujan's theta operator here. And so you want to take the determinant of this matrix, and that's what a Wronskian is. And so what I'm going to do is I'm going to take this determinant and scale it, like multiply it by whatever constant in order to make the leading coefficient 1. So that's what this constant alpha is. And so when I've done that, I'll use this like math cal W to denote the normalized Wronskian of these things. And if I talk about W prime, then I'm not talking about the derivative of the Wronskian, but rather the Wronskian of the derivatives. Again, if I use this math cal W, then I'm just scaling to normalize that Qseries. Okay, so you have these vertex operator algebras and irreducible modules, and so you end up with a bunch of Qseries, and you look at the derivatives, and then you take this quotient. So that's sort of the setup that I want to try to understand. And so just as like a quick example and background, so I first saw this in a paper of Milas, Mortensen, and Ono from 2008. And I should say, like, in keeping with Michael's comment, I don't actually know things about vertex operator algebras. So I want to avoid that sort of discussion, but I guess like when you look at this Virasoro algebra, Milas, Mortensen, and Ono say that, and I think this comes from the theory of vertex operator algebras, the Qseries that you end up getting as your characters are these, which are the Andrews-Gordon series. And so that's sort of what piqued my interest and got me excited about these things. This exponent here, this power of Q outside, you can think of in terms of the vertex operator algebra, the central charge, et cetera, et cetera. But from my non-VOA understanding brain, I just think about this as like the power of Q that you need to make this thing modular, because that's how it turns out to be. So you have these Andrews-Gordon series, and so we want to study the Wronskians for those things. So I fix a K, and then I have K Q series, and I'm looking at these determinants of derivatives. And so just like as a first example, when K is 2, we have these two Q series, which are quite familiar. They come from they are the Rogers-Ramanujan Q series. So let's see what happens when we compute the Wronskian and the other Wronskian and the quotient. So if I look at W of these characters, then I'll get some coefficient, which I'll get rid of in a moment. And then I have this Q series, which maybe looks familiar. I'm curious, does anyone know what this is just by looking at it?
3 coefficients.
Yeah, it's just 3 coefficients, but it's like a power series, and it starts with Q to the 1/6. So it actually does, if you look at more than 3 coefficients, it does look like eta to the 4th. That's a nice coincidence. And if you look at the Wronskian of the derivatives, then you get this power series. Again, I factored out that leading coefficient because I'm going to get rid of it anyway. And so you get another thing, which is not eta to the 4th. And it's not clear to me without knowing what the answer is, what this should be. So maybe I'll just not guess for the moment. But if you look at the quotient, so I'll take this second line divided by the first line and simplify that, then you get this thing. And I've also gotten rid of those coefficients, -1/5 and -11 over whatever. And so you get this Q series. Anyone recognize this one? This one's maybe even more familiar. That looks like E4. So then I guess the Wronskian of the derivatives is like, E4 times eta to the 4th. So that's what it should be. Okay, so that example worked out quite nicely, and it turns out that that's how it goes. And this is a theorem, or I guess like a cluster of theorems from Antoine Milas and Milas, Mortensen, and Ono. So first, if you look at the Wronskian, the one that was eta to the 4th in the example we saw, you'll always have a power of eta. And we kind of know what to expect in terms of what the weight should be. So it's that power of eta all the time. And if you look at this quotient, which in the example we saw was E4, you will always get a holomorphic modular form of weight 2k. And it turns out that if you look at a bunch of values of k, you'll see that sometimes this modular form that you get is 0. So Milas, Mortensen, and Ono identified exactly when that will happen. And by the way, that actually immediately gives you as a corollary a bunch of partition theoretic identities. And furthermore, if P equals 2k plus 1 is prime, then this modular form has P integral coefficients and it is congruent to 1 mod P. Take a sip of water. So by the way, this is really interesting to me because like in some sense with this congruence in part 4, like you're seeing something like what the Eisenstein series do. And if you look at these modular forms, F sub k, some more, I mean, you don't always get an Eisenstein series like we had E4, but you do get like modular forms that have interesting properties in terms of where the zeros are. So if you look at the Eisenstein series, then its zeros always lie on that like lower arc of the fundamental domain. And we can't prove that that's true for these F sub k's, but numerically, I think a few people have done numerics on this. This was, again, I first read this in Milas, Mortensen, and Ono's paper. Sharon's done a lot of numerics. It looks like these things have zeros that lie on the lower arc of the fundamental domain also, and their zeros interlace the way the Eisenstein series do. That's a guess that nobody can prove. So actually that's why Sharon and I got interested in these, because we like wanted to prove this conjecture that the zeros lie where we think they do. And we have no idea. So anyone can do that. Let me know, because I would be super excited. Okay, so I want to switch gears, I think. I also do not know exactly what's on the next slide. Oh yeah, okay, I was right. So I want to switch gears and switch to a different vertex operator algebra. And so this is some vertex operator associated to the Lie algebra SL2 hat. It's a rational vertex operator algebra. And again, for every fixed value of k, you'll get like a bunch of characters. So these are the characters that you'll get. They're actually, if you fix a k, there are k plus 1 characters. So they all look like this. And so you can play the same game. You can define the Wronskian and the Wronskian of the derivatives and this quotient in exactly the same way. And so what happens there? So this was discussed in a paper of Antoine Milas from like 2007. And he proved that, again, this Wronskian is a power of eta. And again, the quotient of Wronskians is a holomorphic modular form for SL2Z. And again, he can prove exactly when that modular form is 0. And again, if P is a prime of a certain form, here I have 2k plus 3 instead of 2k plus 1, but it doesn't matter really. If I have a prime of this form, then the modular form has P integral coefficients. And I guess the question that he posed is, can we say that it's 1 mod P? Numerically speaking, it looks like this modular form is 1 mod P, but he couldn't prove it. So that's my goal for today. Like, let's prove this. Let's turn this conjecture into a theorem. So yeah, that's the small thing. What time does this talk end?
Yeah, started.
Oh, like 4:35? Or
40, 3.
oh yeah, my watch is still on Eastern time, so I'm super confused all the time. Okay, but I don't know. I had the wrong date on the title slide, so I don't know what day it is or what time it is. Anyway, so I'll do this quickly. So if I back up here, these are the characters I want to study, and there are really 2 keys to the proof. So the first key is the observation that if you just ignore this denominator, then everything works. You get that the modular form is 1 mod P, and it's easy to prove. So first I'm going to ignore the denominator and pretend like that's okay. and prove the congruence I want. And then second step, I have to convince you that it's okay to ignore the denominator. That is not easy. Well, that was not easy for me to figure out. Okay, so if I ignore the denominator, then I get these things that I'll call theta. And I argue that proving that the quotient of Wronskians is relatively painless for this theta. So what happens is you take the k plus first derivative. That's because that's like the last row in the W prime matrix that you're taking the determinant of. So here I am computing the k plus first derivative, and I want to reduce this mod p, which is 2k plus 3. So I have n to the 2k plus 3, so n to the p, and then this denominator is 2 to the p minus 1 over 2. So the numerator from Fermat's little theorem is easy to understand, and the denominator is just some Legendre symbol. So if I factor out the Legendre symbol and say that this is n mod p, then I get this congruence mod p. So if I look at this quotient of Wronskians, then I'm looking at the determinant of two matrices. So these are the two matrices you have to study. And okay, so these matrices are the same, or they have all the same rows at least, except on this side, I've got this stuff. On this side, I've got this stuff in the last row, and all the other rows are the same between these two matrices. So the previous slide told me that the first row of this matrix on the left is congruent mod p to up to some sign difference, the last matrix on the right. So when I take the Wronskian of both sides, then I'm going to get the same thing up to some sign difference, but because I'm normalizing, that sign doesn't matter. And so that tells us that the Wronskians are congruent mod p. So when I divide, then I get the congruence that I want. Okay, so that's the key observation. That's step one. And then the second step is to try to convince you that if I do this process, not with theta now, but with theta divided by eta cubed, that nothing really changes. Okay, so that's my goal. So I have to study the Wronskian and the Wronskian of the derivatives. And the Wronskian is actually really easy to understand because there's a standard fact from, I don't know, like differential equations or whatever, that tells you that if you multiply each of these things by the same function f, then you can just factor that out of a Wronskian. So that tells us that if I want to take the Wronskian of these characters, then I'm dividing each term in here by eta cubed, and I can just factor that out. Okay, so that helps me understand what's going on in the denominator of that f modular form that I have. And so now I need to understand what's happening in the numerator. In the numerator, I can't use the same trick because you're differentiating first before you do the Wronskian. And so when I look at the derivatives of these things, then I have to do the quotient rule. And then when I do the quotient rule, my numerator is going to have two terms in it, low d high minus high d low, or whatever we tell our calculus students. And so things will get more complicated. So that's why I can still factor out this eta cubed that's in the denominator, but now I have two terms here coming from that quotient rule calculation. Why is it 1/8 times E2? It's just because that's the logarithmic derivative of my denominator eta cubed. Okay, so basically, I want to show now that this Wronskian here is the same as the Wronskian of just theta prime in each entry. So looking at the matrix that I need to understand, it's this one. So every time I go from one row to the next, I'm taking a derivative, and I have to do the product rule every time. And so I'll just get more and more and more terms to try to understand as I go down the matrix, or at least more and more terms that I need to understand mod p. right? Because I only need to prove a congruence mod P. So this is where I was stuck for an embarrassingly long amount of time. And it's hard to figure out, or it was hard for me to figure out the right way to think about this determinant. So what I decided is that you can actually simplify this matrix, or at least this determinant, as follows. So like if I take the second row and add in 1/8 times E2 times the first row, then that's going to like eliminate these middle terms all along the second row. And then in the third row, the same kind of thing is going to happen. If I do some elementary row operations, like adding multiples of the first two rows to the third row, then I can make it look simpler. And so I'll end up with a new matrix that has the same determinants, because I'm just doing elementary row operations like, you know, sophomore linear algebra style. And I end up with this thing where every entry in the matrix looks like some, you know, like ith derivative of theta minus some other multiple of theta, where these f's are like quasi-modular forms that I can describe using this recurrence in a really succinct way. Okay, so now I've just restated what I need to do in terms of this statement. If I can prove, and it seemed numerically to be true, if I could prove that the f sub k plus 1, so this one in the last row of the matrix, is congruent to 1/8 to the k plus 1 mod p, then that would mean this last row just consists of all things that are congruent to multiples of theta sub 1k, theta sub 2k, etc. You know, because these things are also congruent to theta sub 1k, theta sub 2k, etc. And so that would like greatly simplify the last row, and then I could add multiples of that last row to all the prior rows to get, you know, the matrix that I want. And so that would be like that is the key to getting this last fact. Okay, so now assuming this lemma, just for the moment, I'll talk with whatever time I have left about how to prove that lemma. But assuming for the moment that that's true, then I have a statement like this. And so I can put it all together as follows. So I'm looking at the Wronskian of these characters. And from not last slide, but like 2 slides ago, I proved that these two things are equal. That's from like the basic fact about Wronskians. And now this thing is congruent mod p to this thing from, oh, the thing that I said was painless, the first key observation I had. And then this last congruence mod p was what we did on the previous slide. And so that tells me that the Wronskian of these characters is congruent mod p to the Wronskian of these derivatives. And so when I take the quotient, I get 1 mod p. Okay, so hopefully, modulo proving that lemma, we have proved the conjecture. Okay, so what about this lemma? I'll be quick, I swear. So this is what we want to prove. These f's are defined using this recurrence, and I want to prove that when p equals 2k plus 3 is prime, then f sub k plus 1 is congruent to this constant mod p. How do you do that? Well, you have to rewrite these f's in terms of some recurrence. I mean, thinking about where this term 1/8 times e2 comes from, well, it comes from differentiating eta or eta cubed. And so that gives me an alternate way of stating this recurrence. And then I can use this to sort of rewrite this f sub n quasi-modular form this way. So if I want to compute f sub n now, then I just take eta cubed, I apply Ramanujan's theta operator n times, and then I divide by eta cubed. That's it. And so what do I want to do? I want to understand what this is, mod p, when n is 2k plus 1. So that's what's happening on that last line of the matrix. So that's what I need to prove now. And that's quite simple because eta cubed has this really well-known expression, I can just look at what the k plus first derivative of this is. And so I end up with this. And so I want to simplify this mod 2k plus 3. So in the numerator, I can just apply, again, Fermat's-Level theorem, because 2k plus 3 is my prime p. And then in the denominator, well, the denominator I can just factor out. So I'll just put it right there. So now I have the 1/8 times 1 over 8 to the k plus 1. I have this eta to the minus 3 from before, and I've just applied Fermat's-Level theorem. And it looks now like this Q series that remains is really just eta cubed. So I have this constant times eta to the minus 3 times eta cubed, which simplifies to 1 over 8 to the k plus 1 mod p. And that's the proof of the lemma. Okay, so I mean, yeah, that's it. We conjecture proved. So I think that's a great way to like end the long or longish talks of the conference. That at least in this case and in the Milas, Mortensen, and Ono case, we have this congruence mod p, and now we can prove it. And I'll stop there.
Are there any questions from Rudy?
Has there been work on other vortex algebras in which this is very far from the truth?
There is work on other vertex operator algebras. Okay, so I'll sort of say some things about what I've seen happen and not happen. I don't know, again, I'm not an expert on VOAs, but my impression is that it's common, as long as your vertex operator is relatively well behaved, it's common to have these modular forms f sub k. It's not always true that you get some congruence mod p in certain places. And this thing about where the zeros lie is also not always something that you'll see. Again, in this case, so like we talked about 2 examples in this talk, in both cases, it looks like the zeros appear on that lower arc of the fundamental domain, but we can't prove it like in any situation. If you don't have a rational vertex operator, it looks like there are situations, at least where you get a modular form for some congruent subgroup. And I don't know if there are, I don't know if there are like situations in this world where you would not get a modular form of any kind. I'm not knowledgeable enough to say for certain one way or the other on that.
If you don't mind, I'll ask another question.
Yeah.
So I don't know what Vortex algebras are, but okay, so to prove that what we get from the Wronskian division is a modular form, is that a pure computation, or is there a deep reason why these things all quite deep? Because you said you've always seen them be modular forms. Is there a deep reason, or is it just like computation? Very unfortunate.
This is a good question, and this is one of the things that Sharon and I are trying to make sure that we understand. So I'll tell you my belief, and I don't know, is Antoine in the Zoom room? If you are, Antoine, maybe correct me if I'm wrong. But so my impression is that it really comes from the fact that these characters that you have to start with are like that they span some vector space that what is the word? Not fixed, but you know, like when you apply matrices in some congruent subgroup, like you stay within that. What is that word? Yeah, stable. Yeah. So because this space is like invariant under the action of SL2Z, then, you know, at the end of the day, you'll get like a modular form for SL2Z. And if you have some congruent subgroup instead, then you'll have a modular form for some congruent subgroup. That's I don't know if I've read that sentence like explicitly, but that's from the proofs I've read, that's kind of like the impression I'm getting. Yeah.
Someone's in the chat.
Oh. Invariant, yes. Yeah.
Other questions for Marie? Yeah.
So you said earlier work of Milas with a similar congruence result. So is the proof similar to yours in that case, or is it somehow simpler?
Yeah, so the Milas, Mortensen, and Ono case where they prove their congruence is one mod P. I think it has the same flavor where you like look at the matrix for the Wronskian of characters and you look at the matrix for, you know, their derivatives, and then you sort of, in their case also, you can make this like connection between the two, or at least mod P. In their case, they didn't have to do this like business with ignoring the denominator and then making sure it was okay to put it back in. So that's like the extra wrinkle that we had in this example. And I think that's why it was a conjecture of Milas's, not a theorem.
Other questions?
So you say that you were still looking over where these functions fk, where they go to 0. This is still.
Yes, so Milas proved when they are identically 0. So like for what values of k will your modular form be always equal to 0? But so that's understood. But the thing that's not understood is given a k, you have some modular form that's non-zero. Where does it vanish? That is not understood. Yeah. And I think Milas, Mortensen, and Ono talk a little bit about that in their paper. So I really love that paper. Everyone should read it.
There are no other questions. Let's thank Marie again.